We now want to move from our discussion of measures of central tendency, which included mode, median, and mean, and move to measures of variation, sometimes called measures of dispersion. And there are two that we're concentrating on. One is called the range, and the range is very easy to calculate. It's simply the largest value in the data set minus the smallest value in the data set. And now notice it doesn't take into consideration all of the values in the data set, only the largest one and the smallest one. But it's very easy to calculate, and it gives us an idea about the variation within our data set. All right, another probably much more important measure is called standard deviation. And a kind of loose interpretation of standard deviation is average distance from the mean. And the great advantage of standard deviation is that it takes into account all of the data values. And I can best show you how to calculate range and standard deviation and how it's important to have those two measures in a data set with an example. Consider this problem involving the heights of basketball players on two different teams. Notice first of all that on team 1, the players' heights vary from 6 feet to 6 feet 6 inches. On team 2, however, we have a player that is 5 feet 7 inches tall, shorter than any player on team 1. We also have on team 2 a player that's 7 feet tall, which is taller than the tallest player on team 1. Now let's make some calculations. We're going to make calculations in terms of measures of central tendency and also some measures of variation. To perform the calculations for these measures, let's change our heights into single unit measures. Instead of thinking in terms of feet and inches, let's think in terms of inches only. So the 6-foot player would be, let's see, 6 times 12, that's 72 inches. 6 feet 1 inch, that would be 73 inches. And in a similar way, we would change all of the heights on both teams into inches only, and that will allow us to look at the data sets a little bit more clearly. Well, first of all, let's think about median. The median on both teams is 76 inches. That's the middle item in both data sets. The mode also would be 76, incidentally. But so that's the same on both teams. And now to calculate the mean, we would need the sum of the data values on both of the teams, and it turns out that they're exactly the same. Now we can make the calculation for x bar, which is the sum of x's over n. That's 375 over 5, or 75 inches. The important thing here is that the mean and the median are identical for the heights of the players on both basketball teams. So from just looking at those two measures, we would think, gee, there's no difference in the heights of the players on those two teams. We might be led to think that at any rate. Well, let's make our first calculation in terms of measures of variation, the range. Now, for the range, you know, we take the highest data value and subtract the smallest data value. And for team 1, it would be 78 minus 72, or 6 inches. For team 2, it would be 84 minus 67, or 17 inches. So we're seeing a difference now when we look at this measure of variation, or measure of dispersion. So we see quite a bit larger range value for team 2 than team 1. Now let's talk about standard deviation. We can think of standard deviation as average deviation from the mean. This is a pretty good way to think about it when we think of the logic involved in the equation or the formula that we're going to use to calculate deviation from the mean, or average deviation from the mean. We'll start with, now we're going to take these one team at a time. The heights of the members of team 1 are listed here. And we're going to calculate deviation from the mean. Well, in order to calculate deviation from the mean, we have to calculate the mean. And we did that a little bit ago. But in setting up your problems to calculate standard deviation, one of the first things you need to do is calculate x bar, the mean. So we would add the items in the data set, And those items we found earlier to be 375. Dividing 375 by 5, we find x bar to be 75. Now we can begin to fill in the next column, the x minus x bar. X minus x bar for the first item would be 72 minus 75. 75 you see is x bar. So 72 minus 75 is negative 3. For the next item, it would be 73 minus 75, or negative 2. And in a similar way, we can make the calculation for all of the other values. It's kind of significant to notice that if we add these, we get 0. And this will be true for any data set, that the deviation from the mean, if we add all of those deviations, you see, it kind of makes sense that there would be just as much value above the mean as below the mean, so when we add them we would get 0. So we're not going to find this average deviation from the mean by adding up all of the deviations and dividing by n. We have to do something else, something that might change these values to positive values. Well, one way to do that would be to square all of them. So let's make another column, and we'll call these squared deviations. And the notation would be x minus x bar quantity squared. And for each one, then, we would square, and then we can find the sum of those items, and it turns out to be 24. And now we can find an average, but that average might be the average of squared deviations. Now this is a rather important item in statistics, the average of squared deviations. The notation for average of squared deviations is s squared, and the name for the average of squared deviations is variance. So we're calculating variance. Now you would think that we would take 24 and divide by 5, but it turns out that we take this sum of squared deviations and we end up dividing not by n, but by n minus 1. And there's a particular reason for this, and we probably need to get a little further along in our discussions to understand this fully. But it is this, that division by n tends to underestimate the population variance, but division by n minus 1 does not. Now why is this important? Well, a lot of times we're trying to estimate some information about the population from information about a sample, as we have discussed earlier. And in this circumstance, if we take the variance of a sample, we want that sample variance to emulate the population variance as closely as possible, and it turns out that dividing by n minus 1 is a better estimate of that variance. Well, at any rate, this is our relationship then that we're going to use for calculating variance. And when we pop this into our calculator or make the calculation here, it's 24 divided by 4, or 6. Now we're ready for standard deviation. Standard deviation is symbolized with an S. Now if it's symbolized with an S, and remember the variance was s squared, so if the standard deviation is s, it would make some sense that the standard deviation is the square root of s squared, or the square root of the variance. And that means then it's the square root of 6 for this problem, which is approximately 2.45 inches. Now we'll put this 2.45 inches into perspective a little bit later. Right now, let's think about the steps that we went through to calculate the standard deviation. We began with our data set, and then we calculated our mean. But to do that, we needed the sum of the data values. So we found the sum of the data values, we calculated the mean, and then we set up the table. And in the table is a column for deviation from the mean, and then squaring all of those deviations from the mean. And then we add those values, and we're ready to go with the calculation with the formulas. Now, concerning the formulas, let's think about our relationships here and how we can consolidate matters a little bit. A lot of times it's nice for us to talk about variance when we first talk about standard deviation. We want the logic flow of what we're doing, because if we're trying to remember this on a test, let's say, or later in life, let's say, or whatever. It's important to go back to concepts in order for that memory to be trip-started. And here, if we think of standard deviation as average deviation from the mean, then the logic pattern flows through what we have done in this problem. But we can consolidate things quite a bit here. We notice that if this is an s squared, and here's an s squared under the radical, then we can put the entire fraction under the radical, you see. So we can have one formula for standard deviation if we wish to consolidate in that fashion. Let's go through the situation with the other data values, the data values for Team 2. Here are the heights that we talked about earlier, and they're in inches. And remember, the first task is to add those items and then calculate x bar. So we would write the equation for x bar and then make the calculation. Then we figure out the deviation from the mean. And I'm putting a sum here just for emphasis. We know that the sum of those deviations from the mean is going to be 0. Then we square those values and add those squared values, and now we're ready to apply to the formula. So it's the square root of 156 over 4. Don't forget now that in the denominator there under the radical it's n minus 1, and n is 5 in this case, so the number is 4 in that denominator. 156 divided by 4 turns out to be, I think it's 39. The square root of 39 is approximately 6.24. So the standard deviation for Team 2 is approximately 6.24 inches. Recall that the standard deviation for Team 1 was approximately 2.45 inches. And we're seeing a larger standard deviation for Team 2, which had a bigger range of values, you see, for those different heights. And in general, we can say this, that the more variation there is in a data set, the larger the standard deviation. That's just a simple truism having to do with statistics. Let's talk about shortcut formulas. I'm going to show you two of them here. It turns out that the shortcut formulas are handy because we're going to often be using a calculator for making the calculations involved in calculating standard deviation. Sometimes we can do it very quickly. Other times we have a little bit more to do, but we certainly don't want to just do it by hand in all cases. The troublesome part of the calculation of standard deviation by the formula that we've just used is the x minus x bar column. If there are a lot of items in the data set, then we have an awful lot of work to do. And it's easier to do some other calculations than it is to do the subtraction business, because it involves a lot of entry and manipulation. So if we can just press one button like for squaring, it would help us a great deal. And it turns out that we can trade in this subtraction for squaring in this way. Now just think about our standard deviation formula like this, and I'm just substituting the numerator under the radical with SSX. Now that SSX is the sum of squared deviations. That's what it was, you see, in that original formula. Well, it turns out that if we take that SSX, which is the sum of squared deviations, and perform some algebra on it, that it's equal to the sum of x squared. Now that's the sum of x squares, the sum of all of the x values squared, you see, the sum of a column that would be composed of that, minus the sum of the x's all squared over n. You see, now we can make this substitution. I'll show you how it works in just a minute, and you'll see exactly what this all means. But we can make a substitution here, and in place of the SSX, put this sum of x squared minus sum of x all squared over n, and we have this. So we can use the formula in this way. Now there's another way. We can simplify this even further. Notice there's a sort of a fraction within a fraction here, and we can simplify that. Although it's okay to use this formula just as we see it right here. But another way to think about it, if we just multiply under the radical now by n over n, we would get some nice cancellations, and we have a simple fraction, or perhaps some could argue that it's a simpler fraction under the radical. So either of these formulas would be okay to use for calculating the standard deviation. Let's revisit our two data sets now and use the two formulas and see what I mean by how much easier they are. Now, we're starting out with the heights of the members of Team 1, and notice that I have created a column for x squared. Well, before we go over to that column, we would want to add the heights in our first column. So we add the x's, and we get 375 as we did before. Now, that is the summation of x. That's the sigma x, or the sum of x values that appears in the formula at the right. Now, in the x squared column, we just square each of the items that we see to the left, and then we add them at the bottom. And what that sum is, it's the sum of items that are x squared. So it's a sum of x squares. And that also is an item that is in the equation to the right. And so all we do is just use the formula just under the radical. The first item that we see is the sum of x squared, and we see that at the bottom of a column, so we just bring it over. And then we bring over the other item, you see, the sum of x's, and that number is to be squared. And the number of items in the data set is 5. And then in the denominator, we have 5 minus 1. And then it's a matter of punching the calculator from here, and punching it correctly, we would find our standard deviation to be approximately 2.45 inches. Well, let's look at the other formula in a very similar way. It's very easy to use. We set up the columns in the same way that we did before. And the first thing that we do is add the heights, and then we do the squaring for each of the items. We add those values, and then we're just taking numbers from the bottoms of these two columns to put into our formula. So let's see, n is 5. The sum of x squared turns out to be 28,281. Sum of x is 375, and that number is to be squared. And then in the denominator, it's just 5 times 5 minus 1. Once again, it's just a matter of using the calculator properly, and we find our standard deviation to be approximately 6 24/100 inches for the heights of the basketball players on Team 2. The formula for the standard deviation of a sample is a little bit different from the formula for the standard deviation of a population. Just to put the formulas in perspective, take a look at this diagram. I've got sample formulas over here, and I've got population formulas over here. And for the mean, we've talked about this before, but the sample mean is x bar, and it's the sum of x values over the number of items in the data set. And the population mean is designated with mu, and it's the sum of x values over the number of items in the population, and that number of items in the population is an uppercase N. Fundamentally, though, these are identical. Now, for standard deviation, there's a little bit of a difference. For standard deviation, remember, it's designated with S if we're talking about the standard deviation of a sample. And from our basic fundamental idea, it was the sum of squared differences, remember. Sum of differences from an x value to x bar squared. So sum of squared differences over n minus 1. And we talked already about why it's n minus 1 and not n. The designation for the population standard deviation is this. It's designated with a lowercase sigma. Now remember, the uppercase sigma was this sigma notation for summation. Lowercase sigma is this, and that's the standard deviation for a population. And in making the calculation, notice that instead of x minus x bar here, it's x minus mu and squared and the sum of those values. So it's again, it's the sum of squared differences or distances. And then we're dividing, though, by n, and that's probably the most significant difference between these two formulas. Is here we're dividing by the number of items in the population, and here we're dividing by n minus 1, the number of items in the sample less 1, you see, for the sample standard deviation. Okay, subtle difference. Let's talk about coefficient of variation. This is a technique that is useful to express the standard deviation as a percent of the mean, you see. And it kind of levels the playing field, because when we're talking about a standard deviation for a sample or a population, generally there's a unit of measure. When we were talking in the previous example about the two basketball teams, we were talking about some number of inches, you see. So a unit of measure is associated with the standard deviation. And this takes the unit of measure out of play and kind of levels the playing field if we have a number of different things to compare. Now, for samples, the coefficient of variation works like this. It's the standard deviation for the sample divided by the mean of the sample. So standard deviation divided by mean is all there is to it. Multiply by 100, tack on a percent sign, and we're done. For team 1, from our previous example, it was the coefficient of variation would be, let's see, the standard deviation was the square root of 6. Now we rounded it, but this is an exact value for that standard deviation. So a square root of 6 over the x bar, the mean was 75. And multiplying times 100, we would get approximately 3.3%. And that means that the standard deviation is approximately 3.3% of the mean, you see. Now for team 2, and we're going over this way, this is a sample, we'll think of these as samples. For team 2, the coefficient of variation is the square root of 39 over 75, all times 100, and that turns out to be approximately 8.3%. Now, you see, we can make this comparison between these two without using inches in that comparison. We could see a nice comparison before, and the significance of using coefficient of variation will become more evident later. But at any rate, this is a way of comparing the relative difference in standard deviations for these two samples. For populations now, the formula is pretty much the same, except the notation is a little different. Here for samples, remember, it's S for standard deviation, X bar for mean, and over here for the populations, it is sigma for standard deviation, mu for the mean. And that's the only difference. Rather interesting study was made by a fellow named Chebyshev. Chebyshev's theorem is based upon the idea, he studied the idea of how many items in a data set are within a certain distance from the mean, and that certain distance from the mean being measured in standard deviations. Let me show you what I mean with an example. Remember, with team 1, if I make a graph of the heights of players on team 1, and these are inches along the graph, and we had one player that was 72 inches tall, another that was 73 inches tall, two players 76 inches tall, and another 78 inches tall. Okay, we found that the mean in this sample is 75. So 75 is the X bar. I'll put 75 up here. Okay, so that's the mean. Now, notice what happens if I take a distance of one standard deviation on either side of this mean. Now let's see, the standard deviation was approximately 2.5 inches. I'm loosely approximating this. It was actually 2.449 and so on, so I'm actually rounding up to the next highest tenth, so 2.5 inches. Now, and I'm doing that for ease of calculation. From the mean, I'm going to go one standard deviation on both sides. So I'll add 2.5 to 75. Let's see, 76, 77. That'll be right here. Now, this then is X bar plus S, plus one standard deviation. And if I go in this direction, I'm subtracting 2.5, so 1, 2.5. That'll be about right here. So this is X bar minus a standard deviation. Now, notice how many, this fellow studied how many items in the data set are within certain distances. And here within one standard deviation we have several of the items in our sample. Let's go another standard deviation away in both directions. Now in this direction I'm adding another 2.5, 1, 2.5, that's out to here. So this is x bar plus 2 standard deviations. And in the other direction, here we go with 2.5 in this direction, 1, 2.5, that's here at 70. So this is really x bar minus 2 standard deviations. Now notice that all of the data values are within 2 standard deviations, you see, of the mean in this particular sample. All right, now the calculation for this can be made either algebraically or geometrically. This is a geometric approach. We're looking at a picture, you see. So that's one way to do the analysis. Another way is strictly algebraic. We could say, okay, for team 2 we had these data values. X bar was 75, S, the standard deviation, 6.2. And if we want to make our calculations, then x bar minus S, you see 75 minus 6.2, 68.8. And x bar plus S, 81.2. So we have sort of a range of values here. Let's go another standard deviation away. X minus 2 standard deviations, or x bar minus 2 standard deviations, 62.6. Now notice that this value is actually smaller than the smallest value in our sample. And if we take x bar, the mean, and add 2 standard deviations, we get 87.4. And this value is actually larger than any value in the sample. And so all of our sample items are within 2 standard deviations of the mean. Within 2 standard deviations of the mean. Now, will this always be the case? It was the case in these 2 samples where all the data values were within 2 standard deviations of the mean. That's what this fellow studied. And he found that for any data set, this is true. That he says that we can calculate the percent of values that are within a certain number of standard deviations from the mean by using this relationship, 1 minus 1 over k squared, where k is some number of standard deviations, and we can rely on this as long as k is greater than 1. Now, it could be 1.1 or 1.2 or 1.5, but let's stick with whole numbered values or whole numbers of standard deviations from the mean and see what this fellow came up with. If k, let me start a little bit further to the left here. If k is, let's say 2, then we have 1 minus 1 over 2 squared, or 1 minus a quarter. That's 3/4, or 75%. So Chebyshev is saying that in any data set, 75% of the data values will be within 2 standard deviations of the mean. That's kind of important. We'll see why later. But this conjecture or this theorem is probably more significant in its generality than in its specific. That is, specifically as it applies to, it doesn't apply real well, does it, to the 2 teams that we had over here. Those data values, it didn't really apply too well because it wasn't 75% of the data values that fell within 2 standard deviations of the mean. It was all of the data values that fell within 2 standard deviations of the mean. And often it will be the case that more than a certain percent will fall within a certain number of standard deviations from the mean. But his conjecture is, or his theorem is, that at least a certain percent will fall within that, that range. And that's what makes it so important. It doesn't make any difference how skewed the data set is, that the conjecture will hold true. Okay, so at least 75% of the data values will fall within 2 standard deviations of the mean. Now let's go a step further. How about a k of 3? How many data values can we capture if we are 3 standard deviations from the mean? You see on either side. It is 1 minus 1 over 3 squared, or 1 minus 1/9, or 8/9, which is approximately 89%. So if we go 3 standard deviations from the mean, we're going to have in that range approximately 89% of the data values. And it'll turn out that when k is 4, we can calculate that the amount is approximately 94% of the data values will be in that range. So this just gives it really gives a relative idea. We begin to develop a feeling for the significance of a value in a data set that is 2 or 3 or 4 standard deviations from the mean. How significant is that? How significantly does that value, if it's 3 standard deviations from the mean, how significantly does it differ from the main body of items within the data set? We'll begin to get a feeling for that as we go along and study this further. The United States Weather Bureau has provided the following information about the total annual number of reported tornadoes in the United States for the years 1956 to 1995. And here we see those numbers of tornadoes for those various years. This problem has several parts. The first part says use a calculator with mean and standard deviation keys to verify that the mean number of tornadoes per year is 730 with a sample standard deviation of 172 tornadoes. Pressing stat on the calculator allows us to enter the information, and here we have edit. We want number 1 to edit. So we'll either press 1 or enter. I'm pressing enter, and you see that I've already entered the information. The information can be entered into any of the lists. If you already have information on L1, enter it on L2 or L3. The only difference is if we don't enter on L1, we'll have to tell the calculator where the information is. I'll show you that in just a moment. Pressing stat now, we want to calculate, so I'm pressing the right arrow button. We want one variable stat, so we'll press enter here, or number 1. And this is where we would need to tell the calculator if the information is in a list other than L1. If we want to tell it specifically the list, then we press second function and then something like, oh, let's say item number 3 is L3. So second L3 would tell the calculator to look in list 3. Now, of course, we don't want to do that for this particular problem. I'm going to backspace a little bit here and go second L1 because that's where our information is. And this is the default, and we really don't have to enter this, but I'm doing so just for emphasis. Pressing enter, here is the information we're looking for. Notice the mean is as was stated. We're verifying that it is at 730, so the mean number of tornadoes is 730. The standard deviation, now, it's S subscript X for the sample standard deviation. This is a population standard deviation. This is sample standard deviation. And as was mentioned in the problem, it rounds to the nearest whole tornado at 172. The next part of the problem says to use Chebyshev's theorem to find an interval centered about the mean for the annual number of tornadoes in which you would expect at least 75% of the years to fall. At least 75%. Now, we know from our discussion of Chebyshev's theorem a little bit earlier that at least 75% of the data values will fall within 2 standard deviations of the mean. And that means this for this problem, that if we identify the mean as 730, a standard deviation of 172, that if we go, let's see, 1 standard deviation on each side, 2 standard deviations on each side, that if we go that distance, we will contain at least 75% of the data values. And now all we need to do is make a little calculation. And the calculation is x bar, the mean, minus 2 standard deviations. And on the other side, the mean plus 2 standard deviations. On the left, the x bar minus 2 standard deviations is 730 minus 2 times 172, which is 386. And on the right side, the mean plus 2 standard deviations is 730 plus 2 times 172, or 1,074. And the interpretation of the situation is that at least 75% of the years will have between 386 and 1,074 tornadoes. Now, for our example, many more years than that fall within this range, but nonetheless, Chebyshev's theorem says at least that many will occur in this range. The next part of the problem says to use Chebyshev's theorem to find an interval centered about the mean in which you would expect at least 88.9% of the years to fall. Now, we talked about this 88.9%, and I used the approximation of 89%, that this correlates to 3 standard deviations from the mean on both sides. And you may forget that, though, from time to time. You may think, well, gee, how many standard deviations are we talking about here for 88.9% of the data to fall? And we can make that calculation, actually, by using Chebyshev's theorem directly. His conjecture is, or the theorem says, that that the interval, or the number of standard deviations, is given by k, and k is greater than 1 in this expression 1 minus 1 over k squared. And this is for any distribution of information. Now all we need to do is set this equal to 88.9% and solve for k. And what we're solving for as k is the number of standard deviations from the mean that will contain 88.9% of the data. Well, the first thing we'll want to do is change 88.9% into a decimal, and then we'll multiply through by k squared. Multiply every term by k squared to clear that k squared denominator. Then k squared times 1, of course, is k squared, and the k squares cancel in the second step, and or in the second term, and on the right we'll get 0.889 k squared. Now we'd like to put the terms involving k squared on the one side and the 1 on the other side, so we'll subtract 0.889 k squared on both sides and add 1 on both sides, and we get this. Now we want to collect the terms involving k squared, and we need to remember that that leading k squared is really 1 k squared because we're collecting coefficients. It's 1 minus 0.889, and that gives us 0.111 k squared. And then dividing on both sides by 0.111, we find k squared to be 9.009. And then the square root on both sides, we find k to be 3. Now, it's not precisely 3, it's 3.00 and so on, but it's very, very, very close to 3. So the number of standard deviations here is 3, and this is what we kind of expected if we were familiar with Chebyshev's theorem. Well, we'll go through then and answer the question, and we can make the calculation sort of geometrically as we did before. We can think about it using the graph, and we'll do that in a few minutes, but before we do that, we might make the calculation strictly algebraically. And to do it algebraically, we know that the range we're talking about is the mean minus 3 standard deviations to the mean plus 3 standard deviations. That's the range we're talking about. So it's 730 minus 3 times 172, or 214, to 730 plus 3 times 172, or 1,246. So we're expecting the 88.9% of the years to fall within this range of tornadoes of 214 tornadoes to 1,246 tornadoes. And Graphically, it looks like this. Now, here's where we were before with 2 standard deviations from the mean. If we move out to 3 standard deviations from the mean, we're noticing that for our data set here, all of the data values are within 3 standard deviations of the mean. But we know that Chebyshev is telling us that for any data values, for any set of data, at least 88.9% of the data will be within this range. And we found that range to be 214 to 1,246.